Hello. So today we will be talking about a theorem on probability distribution. We have in fact used this theorem when solving some of the exercises in the previous videos. So let us just have a look at this theorem. It states that let there be a Markov chain with transition matrix P and state space. This one, if P is the probability distribution at any instant, then the probability distribution after one step is P, capital P. In other words, we would have this. Okay, so what is happening over here? If you remember, we are having a state space. This one goes on indefinitely. So we are having a state space A1, A2, A3, and so on up to AN. So the probability that initially, when we are using the word initially, okay, let us think of it in terms of P naught. Okay, so initially there will be a probability attached with each of these states. Let us say it like this: P naught 1. Okay, P naught 1, it's the initial probability that the state will be in A1. P naught 2, it will be the initial probability that the state will be in A2. Similarly, P naught 3, it will be the probability that the state is in A3 initially. But as the system advances, as time over some period of time, the system will not be in the same state. It will change its state continuously. Okay, so after some time, again you can have these possible states. From A1 it can jump to A1, from A1 it can jump to A2, it can jump to A3, it can jump again up to AN. Okay, so similarly from A2 it can jump to any of these states with some probabilities. Of course, if it is not possible that the state can jump from A2 to A1, then that probability will be 0. But still, you can say that there will be probabilities involved as well. Okay, so after one step, again you can have different probabilities that the state can be in A1, another probability that the state will be A2. So let us call this one as P11 after one step. Okay, that the state will be in A1. P12 will be the probability, P21, it will be the probability that the state will be in A2, and similarly up to AN. But again, the system will not be in the same state. Again, it can change. It can be in any state again after another step, after second step. Okay, after the second step, then it can also be in A1, A2, A3. Similarly, there will be probabilities attached with this state now. P21, P22, P23. Sorry, I made a mistake. Should be P12. Second step, and the first probability attached with the first state. P22, the probability after 2 steps, and for the second state. Similarly, we can go on like this. Okay, but what this theorem it says is that if P is the probability at any step, at any instant, okay, so we can take this P over here, it can be the initial probability, it can be this first probability, it can be the second probability, okay, the probability after 2 steps, it can be the probability after 3 steps. But it tells us that the probability distribution in the succeeding step, it can be given by this value, which is PP. Okay, so if you take P to be P naught, then you can find the probability P1, okay, by using P naught P. Similarly, if you take P to be P1, then you can calculate P2 by writing it as P2 equal P1P. If you take P to be equal to P3, let us say, then if you take P equal to P3, then you can calculate P4 as P3P. Similarly, if you take P equal maybe let's say 100, P100, then you can calculate P101, which is P100P. Again, I keep on reminding you that this one doesn't mean the power. It is just a notation. Probability distribution after the second step, probability distribution after the first step, probability distribution after the fourth step, and so on. Probability distribution after the 101st step. Okay, it is not a power. Okay, so let us do this. Okay, so let P equal P1, P2, Pn be this is the proof of the theorem. Let P, P1, P2 be the probability distribution at any stage. Okay, so now, if this is the probability distribution at any stage, which means that P1, it is the probability that the system is in A1 at that stage. Similarly, you can say P2, it is the probability that the system is in A2 at that stage. And similarly, you can say P3, P4, P5, P6, and so on. In general, we can say Pi is the probability that the system is in AI at that stage. Okay, what we want to do. Okay, so after one step, we need to find let U1, okay, maybe let us denote it with another, maybe V. Okay, let us denote V1, V2, Vn be the let Vi. Okay, I'll just denote the Vi be the probability that the system is in AI after one step. After one step, let Vi be the probability that the system is in AI. Okay, so we want to show, let me just say over here, we want to show that V it's equal to P capital P, where V equal V1, V2 up to Vn, P it is this row vector, and capital P it is the transition matrix. So we want to show this one. If we can show this one, then we are done. So now let us first find what is V1. Okay, let us see, and then we can generalize. Now V1, it is the probability that the system is in A1 after one step. So this is actually what is happening. Again, I repeat, A1, A2, initially, okay, at some stage, the system can be in any of these possible states. Even after one step, the system can be in any of these possible states. Okay, P1, it is the probability attached with A1. P2, Pn. Now, after one step, this is the probability V1, V2, Vn. What is the probability that the system is in A1? Okay, so this is what can happen. Firstly, you know that the system keeps on changing. So what can happen is, if we want to find V1, we have to consider that all of them jump to A1. Okay, so this is what is happening. So to find V1, we have to consider that the system can jump from any state to A1. Okay, so hence V1, it will be the probability that the system is in A1 the system is in A1. Initially it is in A1 and then again it jumps to A1 and then it jumps to A1. Or maybe initially it was at A2. So probability system is in A2 and then jumps to A2, to A1. From A2 it can jump to A1. Similarly, we can write this one as or. Lastly, it is in AN, probability that the system is in AN and then jumps to A1 after one step. Okay, so if you calculate this one, so probability that the system is in A1, so it is P1 and jumps to A1. From A1 it jumps to A1, so that's why we can use the transition probability P11 plus, or it's plus and its multiplication, plus probability that the system is in A2, which is P2, and then it jumps from A2, it jumps to A1, so P21, plus it keeps on going like this. So probability that the system is in AN, which is Pn, and then it jumps from AN to A1, which is Pn1. Okay, so actually what we can do over here, I've written it for V1. Similarly, we can find V2. V2, we have to consider that the system is in A1 and then jumps to A2. Similarly, it is in A2, it can jump to A2. Okay, so for finding V2, for finding V3, we can just modify this one a little bit. So what I will write over here, now instead of writing V2, V3 separately, I will just write over here Vi. To find Vi, we have to consider that the system can jump from any state to AI. Okay, hence Vi, probability that the system, so it can jump from A1 to AI, or it can jump from A2 to AI. It can jump from AN to AI. So ultimately, we will be having this one. System is in A1, which is P1, and from A1 jumps to AI, which is A1i. Similarly, P2, P2i, Pn, Pni. Okay, so now we are almost done. Okay, we can actually write this one as summation. Pj okay P okay we can leave it like this. Okay, we can write it in terms of summation. Actually, I think it is best if we write it in this way, hence Vj. Okay, just change it this one to find Vj, okay, it is best if we denote it like that. Jumps to Aj. Over here also we'll just change it. Okay, so this one we can write its summation I equal 1 to n pi Pij. Okay, so over here we are finding Vj, so it's like j its first fix. Okay, what can change its I. Okay, so therefore V1 it can be, okay, I can write this one directly now. Hence V, which is equal to V1, it will be summation I equal 1 to n pi pi1, and then it will be V2 I equal 1 to n pi pi2, V1 V2 V3 up to Vn, which is I equal 1 to n pi pi. Okay, so now we can just multiply. Okay, now let us see. Now, what happens if we take this product P1, P2, Pn, you multiply it with the transition matrix P11, P12, P1n, P21, P22, P2n, Pn1, Pn2, Pn. Okay, so now let us just find this one. So if you see this one, you can actually, so the first entry, it will be this row multiply this column, which will be summation P1 P11. Okay, so it will be P1 P11 plus P2 P21 plus Pn Pn1. The second entry, it will be this row multiply this column, which will be P1 P12 plus P2 P22 plus Pn Pn2, and then ultimately the last entry, it will be P1 P1n plus P2 P2n plus Pn Pnn. So this one, if you see, this one and this one, they are actually the same thing. Okay, so it will be summation I equal 1 to n pi pi1. Okay, because if you see over here, this last entry, it remains as 1, so that's why over here we are having 1 p1 pn. Okay, so this is what is happening. Similarly, this second entry, it will be related to this pi pi2 I equal 1 to n. It can go on like this, I equal 1 to n pi pin. So what can we say from all of this? We have calculated V separately, we have calculated P separately, hence we see that they are equal. So just like I said, if therefore if P0 is the initial probability distribution, then the probability distribution one step later will be P0P. And again, we can have this Pn equal Pn minus 1. Okay, you can actually use this formula because over here, the stage difference over here, it's only one step. Okay, the probability changes from P to V only in one step. Similarly over here, it is only in one step. From P1 to P2, so one step. From Pn minus 1 to Pn, it is only one step. So you can use this formula whenever there is a difference in one step only. Okay, so but combining all this, hence Pn, it will be Pn minus 1p. But Pn minus 1, it can be written as Pn minus 2p. Okay, Pn minus 1, it can be written as Pn minus 2p, and then you are having another p, so you will be having Pn minus 2p squared. You keep on going like this, so ultimately you will be having p0 pn. Okay, so this completes the proof on the theorem about probability distribution. Until next time.